Okay, last time we just started on what was called the golden section search, which is an alternative to dichotomous search that aims to increase the rate of convergence. And central to that is what will turn out to be 1 over the golden ratio, this ratio R, which is a ratio between the small section between the start of the domain and the right-hand point divided by the overall domain width. And by preserving that ratio from step to step, we allow there only to be one function evaluation per call, per step. And that contrasts with the 2 function calls per dichotomous search step. So let's get on with calculating this value of R. Okay, so we've been moving on to this method called the golden section search. And this has involved constructing points x left and x right on our line at any one point, and then observing that the ratio A on B is this, which is this R, which we want to determine, remains constant throughout the algorithm. So as we make the interval smaller, we still can see that this ratio A and B is preserved, and that's the way we keep the number of new points down to just 1, and so that this ratio then is preserved between this length and this length as we go on, and this means that we can have these 2 points in common at each point, and we only have one new function call. So what we started last time was just to derive this ratio R. So really the derivation is all about the setting up of things, and then once you got to the setting up, it's very straightforward, I think. So remind ourselves we have xi right and we have xi left, and one way of thinking of these is a sort of a linear combination or linear weighting of your endpoints bi and ai. So xi right is ri bi plus 1 minus ri ai. So one way to remember this, when r is 1, then xi right is the right hand point, and then xi left is the other way around. So let's just say, let's call this 1, 2, and the main thing that we found from last time, I'll just retain the last part of the brackets, was this ratio at any time was xi left minus ai on xi right minus ai. That's simply this ratio in the second part of the iteration that we showed there. And the algebraic steps then are just substitute 1 and 2 into 3, and this will then eliminate xi left and xi right. Actually it will eliminate ai and bi as well, and we'll just end up with an expression in terms of r. Okay, so let's see if we can do that in this final line here. xi left. No, I think I'll start a new board. Actually, if you're interested where it comes from, so xi left minus ai is this distance here, and xi right minus ai is this distance here, Let's just get the pen up. I can rewrite that in a minute. Just want to. So we're saying that xi left, because of the commonality of the points, x, so we call that A, C and D. We're acknowledging that C on D is R, and that's the best way to start. And you can just, because there's commonality of points, you can see that's xi left minus AI is C. And D is xi right minus AI. Yep. Going back to the board then, Ri is xi left minus AI on xi right. This is for the case where you select the left bracket and it's completely symmetric. The same result would apply if you did it the other way around for selecting the right bracket. And that equals, and we're substituting in our expressions for xi left, so that's Ri AI plus 1 minus Ri Bi minus AI. So that's xi left. Xi right is Ri Bi plus 1 minus Ri AI minus AI. And then we just factorise. So that's 1 minus R I minus AI. I'll become apparent why that is in a minute. So that's plus 1 minus RI BI, and the AI's cancel here, so actually we already have RI BI as AI. So finally we then have this common factor BI as AI, so it's RI. Okay, so it's very simple algebra. So it's setting it up. It's getting this first expression right, and then substituting the expressions into left and right, and then you're fine. It's actually a common bit of bookwork in part A parts of exams. So the B minus A cancel. So we then end up with Ri equals 1 minus Ri on Ri. You know, it's perfectly acceptable to drop the i's if you like, and I'd accept that as a solution in the exam. Again, I'm just doing it for sort of slightly more specific, saying that Ri is undetermined first, and then we set it to R at the end. So this then leads to Ri squared plus Ri minus 1 is 0, a nice quadratic for R. But it turns out the positive roots, so let's just Ri equals minus 1 plus or minus the square root of b squared minus 4ac. So that's square root of 5 all over 2a. But the negative root is meaningless in the context of this problem. It doesn't have any meaning because it means just a negative value, so we retain the positive root, and that's the Ri now, and we're going to call it R because we determined it, equals -1 plus root 5 on 2. Let's just write that up at the top here. -1 plus root 5 on 2, which is 1 over G, and G, where G is the golden ratio, this special number that goes back to the Greeks that they used for architecture. I thought it was a very important ratio. But so this is why this is why it's called the golden, hence the golden section search. So the golden ratio is in there, and it's a consequence of setting the distribution of points between successive sections as they are, and only having one function call. And we can also compute R. R is simply 0.618 to 3SF. And the interval decreases by this factor at each step, and at each step there's just one function call. Now this then brings us back to that result we had for the dichotomous search. So recall dichotomous search, so it should be a capital D, dichotomous search, it reduced by this interval by 1 over root 2, and if we just compute that, that's we'll calculate that, it's 0.707 each function call. Whereas the golden section reduces by 0.618 each call. So for that reason, the golden section search is faster, or slightly faster, and an improvement on the dichotomous search. So it's a modest improvement in convergence rate. And in the process of doing this sort of comparison, we get a sort of deeper understanding about how these methods work. That's almost as much as important as this result itself. So the golden section search is a modest improvement of convergence rate relative to the dichotomous search, and given it's in terms of coding, it's no different. It's a common choice in optimization problems. Okay. Okay, so there's 5 minutes, and I'm going to just start. So that's really completed 1D optimization. for this week, but we're just going to start on moving on to multiple dimension optimization now. Because this is really where, in a lot of big examples, whether it be data science or other examples of modeling with where you've got lots of variables, that the optimization comes into its own. Although the humble line search can be used very effectively within multiple dimension optimization problems as well, as we'll see. And what I might do is just move to some slides for the last for the last 5 minutes. Okay, so here we are, some intro slides, and the concept we're going to be concerning ourselves with is this one of convexity. Okay, and it's all to do with the shape. So a convex in 2D, a convex function is a parabola. This is convex, and if we can convince ourselves that a function is convex in multiple dimensions now, then we know that there's going to be a minimum, a global minimum at this point. So what we're going to spend a little bit of time is clarifying how to show the existence of a minimum before we go and find the minimum. And that essentially will bring us to the end of the module for this term. And after we've done both of those exercises for a number of cases. So we're on the homeward route. So yes, here you are. Here's an example of convex function, something very familiar from way back now. You have your parabola, and it's supposed to be the side, and this is what you call a global minimum. Global means it's a minimum for all values of x in this case. So you've got the function, it increases monotonically either side and it has a zero. But I just wanted to observe that we often look at the second derivative in calculus. So the second derivative being greater than 0 in this case. But what we're going to try, the aim of this next section, the module, is to say, well, what's the result, the equivalent result in multiple dimensions? And this is concave. Yeah. So you have a global maximum. Okay, so that's all very familiar. It's always good to start with more familiar. And this is an example of a convex function in more than one dimension. And this is a very simple one. It's x squared plus y squared. Here I've plot a contour plot where different colours for different values in x and y, and it has a global minimum as well. So this is concave. So, sorry, convex function in 2 dimensions is fairly easy to visualize. In some ways it's a bowl function, and that's the sort of thing we'll be dealing with. So if x star is the minimum in 1D, then f double prime x star is greater than 0 is the, and you didn't call it this at the time, but it's essentially the convexity condition. It's saying actually the the shape of the function is such that and means and if f double prime of x is greater than 0 for all x, then f x star is a global minimum. So that's all very normal calculus, but now the question is, what is the equivalent of f double prime x star in 2 or more dimensions? So the observation in 1D we have d2f by dx squared, right? We don't have anything else. But in 2D we have partial f by dx squared, partial f by dy squared, partial f by dx dy, cross derivatives, and then maybe the other way, but it's the same thing. So how do we use these derivative nouns in second dimension? We will mainly focus on the second dimension, although it's applicable to higher, to try and get the equivalent f prime is greater than f double prime is greater than 0. And this could overlap a little bit with the calculus you did at the end of year 1, if you can remember that, where you're expanding functions in more than one variable. You may have even encountered the Hessian briefly. It may have just been on your question sheet, so I'm going to go back over that. But the thing we're looking towards is something called the Hessian. We're moving towards H, which is the Hessian matrix. And that will play, that and its related quantities will play an equivalent role to f double prime in 1D. Okay, and this is the way we can prove that. So the route forward is we're going to establish that the minimum exists, and then we'll look at methods about how to find the minimum. Okay, see you next time.